Here is an example. Here, same example here. He's asking about find the total active power, reactive power, apparent power supplied by the source as well as the source current. Okay. Here, load 2 and 3 they are connected in series. Load 2 is consuming around 1.2 kilowatt. Load 3 is consuming around 4 kilowatt. I doubt in real world we will have a connection something like this. Very rare cases, most probably 0.001% or something like that. So it's not exactly a realistic example, but for sure this will help you to understand how to calculate how to do the power calculations. Okay, so load 1, the given data, here he gave you 2 kVA. So 2 kVA is nothing but S value. So I'm going to do the load 1, S value S1 is given 2 kVA. Okay, that's called apparent power. uh, there is not much. Apparent power is only one number, real number. When it comes to complex power, this is complex power. Both are in kVA, but the difference is complex power is always P plus JQ, um, and apparent power is only square root of P square plus Q square. Q square, this is nothing but square root of P square plus Q square. Okay, apparent power is only give you magnitude, but complex power always we talk about real and imaginary. Okay, now we know S value and we know cos theta value 0.707. So if I do it by using the power triangle, so it's a leading power factor. So leading means it's a capacitive load. So all I know, this is the S value, this is negative JQ, this is P value. Okay, since I know leading is nothing but capacitive load is nothing but minus JQ, and all I know this angle cos inverse of 0.707, I think that is 45 degrees, so we know this angle. Okay, so I know the angle and I know the S value. From there I can find P value. P equal to, can I say sine theta or sine 45? Actually, P value you can find cos 45 times S. Okay, so that's how I found P value. 2 times 0.707 will end up to 1.414 kilowatt. So this is 1.414 kilowatt, and Q value you will end up with Q equal to sine 45 times S. You will end up with the same thing, 1.414 kVAR, kilovolt ampere reactive. Okay, since this is negative, this must be negative there. I don't know why I put positive there. This value must be a negative. Whenever you see leading power factor, that is supplying Q value, so that must be a negative value. Okay, now load 2, active power is 1.2 kilowatt. Okay, and he clearly mentioned it's a capacitive load. Okay, so capacitive means that is a negative 2. So apparent power must be P minus JQ. So this must be P minus JQ. 1.2 minus 0.8 kVAR. I think he gave you P value as well as Q value. Kilowatt kVAR. Okay, P2 minus JQ2. Okay, now S3, load 3, he gave us 4 kilowatt P value and 0.9 lagging power factor. I didn't draw power triangle for load 2, but if you want to, that's P, that's Q. We know those two values, that's what we care for, so there are no much calculations involved here. Now load 3, it's a lagging power factor, so lagging means for sure it is consuming power. We know this value 4 kilowatt, we don't know, plus JQ, that is S value. Okay, so theta is cos inverse of 0.9. What we have, cos inverse of 0.9, which is 25.84 degrees. Okay, so this is 25.84 degrees. From this I can find Q value and S value. I have Q reactive power, Q equal to 1.937. So Q equal to, can I say tan theta or tan 25.84 degrees times 4 kilowatt. That will give you. So tan theta is opposite over adjacent. So tan theta times adjacent will give you the Q value. I have that value as 1.937 kVA or kilovolt ampere reactive. Q value is always kVA or kilovolt ampere reactive. Now, so you're going to add all three of them together. So S1 plus S2 plus S3. So S1 is 1.414 minus J 1.414. Since this is active power, reactive power is capacitive load, so it is negative. Load 2, same thing, 1.2 minus J 0.8. Active power consumed by the resistor minus 0.8, which is supplied by the capacitive load. This is supplying, basically these two are supplying. And load 3, it is consuming 4 kilowatts of active power, also consuming 1.937 kVAr of reactive power. So the total is 6.614 P, and Q value is, it's only 0.23 minus J 0.276 kVAr. So still the loads are supplying back some energy. So source power factor is P over S. So S is nothing but square root of 6.614 whole square plus 0.276 whole square. That's how I found the S value. Apparent power, I have to use the apparent power. There is not much difference, so power factor is 0.99. Leading power factor, leading because I have minus J there. So that's active power and reactive power. Now if I want to find I naught here, I naught must be, so P equal to total power supplied by, so P total, this is VI cos theta. Okay, I know P total, which is 6,000, how much? 6,614. So 6,614 equal to V, supply voltage is 120 volts, that's the given value, times I cos theta 0.99. The cos theta is total power factor. Okay, so what is I here? So I here is 55.67 amperes. Okay, this is another example similar to previous example, but here loads are connected in different manner. Okay, move on to the next example. Here is the third example. Here, instead of power values, I gave you the impedance values. So three loads are connected in parallel. The supply voltage is 120 volts. So load 1 has an impedance of 3 plus J4 ohms. Load 2 has 8 minus J6 ohms. Load 3 has 12 plus J9 ohms. Okay, so this is resistor, inductor, resistance, inductive reactance, resistance, capacitive reactance, inductance, resistance, inductive reactance. Okay, whenever you see plus J, it is inductive reactance, minus J, capacitive reactance. So for each and every load, we're going to find the complex power. So load 1, which is Z1, I can say, let me find Z1 equal to 3 plus J4. When I convert this into polar format, which is 5 at an angle of 53.13. Okay, now I can, all these three are in parallel, so voltage must be same. So I1 must be V over Z1, which is 120 divided by Z1 is 5 at an angle of 53.13. That must be 24 at an angle of minus 53.13 ampere. Okay, now what is cos theta? Cos theta 1 must be R over Z, which is R is 3 divided by Z is 5, which is 0.6, which is lagging power factor. Okay, that's a cos theta 1. Now can we find same way sine theta 1? Theta 1, so basically this is nothing but sine 53.13. that value is 0.8. Okay, for sine theta you don't need to put lagging or leading, it's only for cos theta. Cos theta is a power factor. Okay, now P1 equal to VI cos theta 1 v1 I1 cos theta 1 v1 is same. So 120 times, just take the magnitude, don't worry about the phase angle. That phase angle is already included in cos theta, times 0.6, that is P1, which is 1.728 kilowatt. Same way Q1 VI1 sine theta 1, which is 120 times 24 times 0.8, that value 2.304 kVAR. Okay, so my S1, I'm going to write it as P1 plus JQ1. P1 is 1.728 plus J 2.304 kVA. When it comes to S, it is in kilovolt ampere. Okay, now load 2, I have 8 minus J6. Load 2, Z2 equal to 8 minus J6, so which is nothing but 10 at an angle of minus 36.86. So that's a capacitive load. So cos theta 2 equal to R over Z, 8 over 10, which is 0.8, leading power factor though, because it's a capacitive load. So from here you can say sine theta 2 is sine 36.86. I'm sure that value must be 0.6. Okay, now can we find I2? I2 must be V over Z2. V is constant, I mean since it's in parallel it must be same. 120 over 10 at an angle of minus 36.86, so 12 amperes at an angle of 36.86. It's a leading power factor. Okay, so once I know I2, P2 equal to V I2 cos theta 2, 120 times 12 times 0.8, that value is 1.152 kilowatt, and Q2 is VI2 sine theta 2, 120 times 12 times 0.6, that value is 0.864 kVAR. Okay, kilovolt ampere reactive. That's load 2. Load 3, we have 12 minus 12 plus J3. Okay, Z3 equal to 12 plus J3, sorry, J9. Okay, which is 15 at an angle of 36.86. Okay, now since that is 36.86, it must be like 12 over 15 must be 0.8. Here it is lagging power factor, and sine theta 2 must be 0.6. Okay, now I2 must be V over Z2. V, I have 120 over 15 at an angle of 36.86, which is 8 at an angle of minus 36.86 ampere. Okay, now my apology, it's 3. Okay, because everything is load 3, but it's 3. Okay, now I3, once I have I3, P3 must be 120 times I3 times cos theta 3, 0.768 kilowatt, and Q3 equal to 120 times 8 times 0.6, 0.576 kVAR, kilovolt ampere reactive. Now when we put them together, I forgot to put S2. S2 has a leading power factor, so it must be 1.152 minus J 0.864. S3 is, since it's lagging power factor, it is consuming active power plus reactive power. Okay, so total S total equal to S1 plus S2 plus S3. Okay, what is the total? I have S1 equal to 1.728 plus J 2.304, 1.7. So here S1 is 1.728 plus J 2.304, S2 is 1.152 minus J 0.864, S3 is 0.768 plus J 0.576. These are all in kilowatt and kVAR. Okay, so the total kilowatt is 3.684 plus kVAR is plus J 2.016. So it is consuming 3.684 kilowatt and also consuming 2.016 kVAR P and Q. So cos theta is P over S. S must be, instead of complex, you have to use the apparent power. So 3.684 divided by 4.199. So 0.877 lagging. Okay, I total equal to P total divided by V cos theta total. So 3684, I converted that kilowatt into watt divided by 120 times 0.877. So I total is 34.99 ampere. Usually current must have angle, so that angle is cos inverse of 0.877, and that value is 28.717. Why I have negative? Because it's a lagging power factor, so current must be negative. Or you can do it as I1 plus I2 plus I3, vector sum of those two, those three currents. We have I1 is, I forgot to, I1 is 24. So 24 at an angle of minus 53.13. I2, I believe 12 at an angle of 36.86. That's positive. And I3 is 8 at an angle of minus 36.86. If you add them vectorially, you must end up with 34.99 at an angle of minus 28.717. This is another way to find the total current. Okay, thank you.